I'm going to give you a talk that's going to be very, very different from this morning's. Okay, so it's going to be a combinatorics talk, but I'm thinking that some of the ideas that we tried to develop in combinatorics could be proven in a better way using some integrable combinatorics method. Okay, so see it as something that maybe you could do better. Okay, probably. Okay. So I chose to talk about that because we just posted the paper on the archive, and also as I'm the one female speaker of the week, I thought that having 3 female collaborators that would balance the global parity of the program. Okay, so it was really great, and it's really great to work with Sarah Bronner, who is at Brown right now and will be moving to UPenn, Zajdo Werty from Reed, and Anna Killing from Leeds. And then we can think also that it's timely because what I'm going to talk about is really crystal bases, even though I'm not going to talk too much about what they are. And we learned yesterday that Kashiwara got the apple. Okay. So I'm going to tell you about a graph. Okay. That's a graph that's indexed by a partition. And the vertices are going to be the standard Young tableau indexed by this partition. And the edges are going to be certain moves that we're going to talk that we can do to go from one tableau. Okay, but before I do that, I'm going to try to explain to you why we want to construct such a graph and where it's coming from. Okay, but first let me just do some advertisement. Okay, because I have the chance to live in 2 places that are really nice and organize things there that are really nice too. So next year in June, with Jérémy Boutier and Sophia Tarikan, we do a summer school at the Sorbonne University named Integrable Combinatorics. And also in the spring 27 at SLMA, so it was MSRI before, there will be a whole semester on algebraic combinatorics. And Lauren is one of the co-organizers of this. Okay, so come or send your students. Anyway, these are going to be, I think, 2 good things. Okay. So what's my motivation here? Okay, so what I'm going to do is I'm going to study, in general, I like to study families of symmetric polynomials. Okay, so I'm going to think of, I have n variables here, x1, xn. My families of symmetric polynomials are going to be indexed by partitions, here I call mu, that have at most n parts. And maybe my polynomials are going to have some extra variables, t1 up to tk. And then I want to express this family of symmetric polynomials in a Schur basis. Okay, so that's in a basis that's also indexed by partitions. Okay, so that's a basis of the symmetric polynomial. And I want to look at the coefficients, okay, when I do the expansion of my family G mu in the Schur basis. So as combinatorics, often we want to know whether these coefficients, so these C lambda mu in k variables, okay, are polynomials in T1 up to Tk, and also especially in combinatorics. So I'm interested whether the coefficients of these polynomials are all non-negative integers. Okay? And so if it's the case, we say that this polynomial is a Schur positive. Okay? from mostly representation theory, because that means that as the show basis are character of PLN, then that means that the polynomial you're studying has some kind of link with representation theory of it.
So it's an indication that it's maybe a character of something.
Yes. I think that's okay. Now I don't conclude that anymore. It's my day. Okay, so then that's the real combinatorial question. Okay, if this is show positive, okay, can we give a combinatorial interpretation of these coefficients? Okay, so then of course this is a, if I can answer the purple question, that implies the green question. So as not all of us here are combinatorialists, let me tell you what I mean by a combinatorial interpretation. So the show basis that I define, that I just stated right before, okay, there's many ways to define this basis. So for example, I can define this as a ratio of two determinants, n by n, okay, because my partition lambda is at most n car. But what I call a combinatorial interpretation is something very concrete, is I can write this polynomial, okay, as a sum on combinatorial objects, and then I give a weight to each combinatorial object. So here I chose something very classical, okay, so this show polynomial lambda, I can write it as a sum on semi-standard Young tableau of shape lambda, where the entries are less or equal to n, and then to each tableau I associate one monomial that comes from the tableau, okay? So let me just remind you, even though probably all of you know that very well. So if lambda is 6, 4, 2, so that's a partition of 12 into at most 4 parts. I write the diagram of my partition. I can do that. So 6, 4, 2, and I fill this diagram with numbers from 1 to 4, such that I strictly increase in column and weakly increase in row. Okay. So that's all. So for each lambda, I look at all the possible fillings of lambda with numbers from 1 to n. And to each tableau, I associate a monomial. And this monomial, actually, I wrote it wrong. Okay, so I called x1 to the number of 1s. So I should have x1 cubed here. x2 to the number of 4, x3 to the number of, x2 to the number of 2, x3 to the number of 3, and x4 to the number of 4. Okay. So that's what I mean by combinatorial interpretation. Okay, I can write what I'm looking for as a sum on some combinatorial object. And to each object, I hope to give it a weight that's going to be a monomial or a polynomial, but always in positive code. Okay. Okay. So let me tell you about many techniques to prove show positivity. So the first one is the main motivation of that, is we know that show polynomials are characters. And so we can think of now these polynomials that we want to expand in a show basis as characters of something, okay, and study them from a representation theory point of view. So using that, for example, what showed that modified Macdonald polynomials or MLT polynomials are show positive. But there's many more combinatorial models. So for example, the RSK algorithm can tell you that Q show functions are show positive. Okay, and then something closer than what we study today, using the crystal graph. Okay, so the crystal graphs were defined by Kashiwara, and I'll explain to you in a type AN what they are. And there's some bunch of axioms that define them in a unique way. And using these axioms, you can prove that certain symmetric functions are shown. So this was done for many symmetric functions. And in particular, Schilling and Morse and Schilling proved it for Stanley symmetric functions that are expansion of like reduced decomposition of permutation. Okay. And finally, after there's some bunch of combinatorial techniques to try to prove this. And very recently, there was a very cool proof. So about the chromatic symmetric function. Okay, so you take a graph and you proper color it, and you associate to each proper coloring a monomial. Okay, and it was known that for unit interval graph, this chromatic symmetric function was show positive. Okay, but in last year, okay, using again standard Young tableau, there was a very cool proof that indeed those things are stronger than show positive. They are also E positive. This is a very fun paper where there's a mix of combinatorics and probability to prove this E positive. Okay, so my question to you, okay, so is it possible to prove show positivity using some vertex models or some models coming from integrability? So this worked really well for skew-show function. Okay, you can interpret the RSK algorithm. There's also some timing models due to Paul-Justin or the Knudsen-Tao puzzle. You can see that as some kind of things coming from integrable models. Okay, but to prove the show positivity of LLT polynomials in the big paper of Agarwal, Borodin, and Wheeler, there was some hope to do that. But what they could do is they could expand them in the modified all little voltage. Okay, so the vertex model were not giving tricks straight away to prove the show positivity, but at least they could be used to expand in another basis, okay, the modified all little voltage. So what I'm going to do today is I'm going to try to build a combinatorial tool where the idea is to prove a show positivity, okay, but for a certain family of symmetric function, okay, so the symmetric function where we know the expansion in the fundamental quasi-symmetric data, okay, so that would not be all the symmetric function, but I want to do that for certain symmetric function where I know the expansion in the fundamental quasi-symmetric. So let me explain to you what I mean by these words. Okay, so the quasi-symmetric function, they are a superset of the symmetric function. Okay, and they are indexed by composition. So we have partitions. Okay, so lambda, the partition into at most n parts. I want the parts of my partition to be weakly increasing. And then I say that lambda is a partition of M if the sum of the parts are equal to M. Okay, and here we have composition. Now I don't have this condition. I don't have their order matter. Okay, so I just have the fact that the alpha i's are non-negative, and the sum of the alpha is equal to M. Okay? And so the fundamental quasi-symmetric function, I guess here I'm just study polynomials. Okay, so they're indexed by compositions. They are polynomials, they have n variables. It's going to be, I'm going to take a weakly increasing sequence of M indices between 1 and M. Okay, and for now I have no dependence on my composition, but if J in alpha, okay, then I must have the fact that ij is strictly less than ij plus 1. Okay, so that forces a certain condition where I guess this I have to define what. So on the slides, I gave you the example of f of 1, 2. Okay. So what do I mean by j in alpha? That means that after 1, I must have a change of index. Okay. So x1, x2 squared, x1, x3 squared, x2, x3 squared, and x1, x2. So this is not symmetric. This is quasi-symmetric. Okay. And the composition tells me when I must have a change of index. And so why the Shor function and the fundamental symmetric functions, fundamental quasi-symmetric functions are related is that we can write a Shor polynomial, okay, as a sum of f, where here we sum on all the standard Young tableau. Okay, so a standard Young tableau is like a semi-standard Young tableau, except that each number appears exactly once. Okay. Get the Shor polynomials from the f. I sum on all the standard Young tableau. And then I associate a composition to each tableau. So how do I get this composition? Okay, so I'm going to read the numbers in my tableau from 1 up to n. And whenever I have to go above or to the left, okay, I'm going to circle my number in green. Okay, so 1 is under 2. Okay, so 1 is circled in green. And then 2, 3, 4, I'm going to the right, so I don't do anything. Then 4, I have to go to the left to go to 5. So 4 is green, and then 5, I go to the right. 6, I must go to the left, and 7, 8. Okay, so that gives me a subset of the numbers from 1 to 7. Okay, and the composition that corresponds to this subset. Okay, so I put 1, and then 4 minus 1, 3, 6 minus 4, 2, and 8 minus 6. So I can associate to each tableau a composition that corresponds to what we call the descent. Oh, I'm not sure how to say that in the. Okay, and I can get back my Shor polynomial by summing on all the standard Young tableau with this descent set. And so, by example, if I want to compute the Shor polynomial of 2, 1, okay, we have 2 standard Young tableau of shape 2, 1, and one will have descent composition 1, 2, and the other 1, 2, 1. So one could think that choosing this condition would be a bit difficult, but actually there's lots of symmetric polynomials where we know the expansion in that fundamental basis. Okay. So for example, the LLT polynomial, okay, it's really an extension of what we did exactly for Shor. Yeah. But if I want to expand the LLT polynomial, so they're not indexed by one partition, but by k partition. Okay. So here x just means my n variable. They have an extra parameter t. Okay, and we can write these LLT polynomials in the f basis as now I sum on a k tuple of standard Young tableau of each shape. Okay, and I have a statistic of co-inversion that I can count on my k tuples of standard Young tableau, and then I can associate a composition just like what I did for Shor. Okay, so I won't tell you exactly how it goes, but it's just a k generalization of what we did for Shor function, and you can get that for LLT. So that's one motivation that we have, is that, for example, the LLT, the modified McDonald, many families where we don't know the combinatorial interpretation in the Shor basis, okay, then we know the combinatorial interpretation in the fundamental basis. So our new tool is what I'm going to tell you today. Okay, is what's called crystal skeleton. Okay, so they come from the work of Masgariepi, that was pretty recent, where she defined actually these crystal skeletons. Okay, and then there was some other work coming from semi-groups that were very different, but that were doing pretty similar things in papers of Montero. So before I define what a crystal skeleton is, okay, let me move that thing. Okay. So let me tell you what a crystal graph is, okay? So here I will define only the type AN crystals, okay, that were defined by Kashiwara in the 90s. It's related to also the work of Lustig around the same time. And but you can define that in merge generality for all for many cases. But here, let's just focus on the very concrete thing of type AN minus 1. Okay, so what's a crystal graph? It's a directed graph, so that we will call B lambda of n, where lambda is a partition of M, and n would be the same as before. Okay. So the vertices are standard, semi-standard Young tableau of shape lambda, where the entries are less or equal to n. Okay, and then the edges between two tableaux are labeled, okay, by raising operators Fi's, okay, that comes from quantum. So I cannot always apply a raising operator on every tableau. Okay, so I have a map from B lambda to B lambda union 0, because sometimes the raising operator just sends your tableau to 0. So let me try to explain to you how you build this graph. So as I said, it's a graph on semi-standard Young tableau of shape lambda, where the entries are less or equal to n. Okay, so each semi-standard Young tableau has a monomial associated to it. But you can also see that as a 5-vertex model. Okay, so using Lindstrom, Gesell-Bielo, you can do a bijection between semi-standard Young tableau and 5-vertex models. Okay, where here the weight depends on which row the cell is, and then I would put a weight xi whenever a path exits to the right. Okay. So now I label my rows x1, x2, x3, x4. Okay. And I go from the tableau to the 5-vertex model just by reading it row by row. So here I have 1, 1, 1, 2, 2, 3. So that means I do 1, 1, 1, 2, 2, 3. Then I do 2, 2, 3, 3, like that. And then I do 3 and 4. There's a 1-1 correspondence between those tableaux and these 5-vertex models, where the shape lambda tells me exactly the arrival point. Now I'm asking you, can I apply F2 to the semi-standard Young tableau? Okay, and so you can apply Fi only if you look at the entries I and I plus 1 in the tableau. Okay, and that tells you whether you're going to apply Fi here. So on the 5-vertex models, I need to look at only the 2 rows that are labeled xi and xi plus 1. Okay, and what do you do after? You look at all the step of label I plus 1, and you try to pair them with a step on the lower level. Okay, so this step I pair it with that one. This one I pair it with that one, and this one I pair it with that one, and this one I cannot pair. Okay. Okay, and the answer, I can apply F2 if and only if on the level I have a step that's left, at least one step that's left alone. Okay, that was not paired with anybody. So if at level I have a step that's not paired with anybody, I could have many of them. I choose the rightmost. This will always correspond to a corner here on my path. And what you do is you flip. Means that on this, okay, I can apply the raising operator, and I change this corner into this corner, and I get this. When I do my pairing like that, there's no free. Okay, that means I cannot apply my F2 operator. And so that's true for every I. Okay, so for every I, if I want to apply Fi, I look at the two labels I and I plus 1. I do this pairing, and if I have a free set at level I just flip this. Okay. So actually, I paid him. Okay, so that means when you go from a tableau to the next, okay, you just have a, so that means I replace an I by an I plus 1. Okay, so I get that xt times xi plus 1 is equal to xu to the u times x. Okay, so that means that if I take an example here where lambda is 2, 1 and n is equal to 3, okay, you can build this crystal graph. And this crystal graph has many, many nice properties. Okay, so namely, there's always one tableau descent where I have all ones in the first row, all two in the second row, and like that. So this is the unique tableau that won't have any edges coming towards it. Okay, and otherwise, I can build this graph for any shape and any end. Okay. And so I don't tell you the representation theory part of the story, but this is how you can study the representation of SLN thanks to this crystal graph. Okay. So these crystal graphs have many, many nice properties. And in particular, okay, you can check whether if I give you a graph with a set of vertices and a set of edges labeled Fi, you can check with certain axioms whether this is a crystal graph or not. Okay, so in type AN, this was done by Stambridge, but that also works with other types. Okay, there are some very strong axioms, and let me give you a couple. Okay, whenever I have a vertex where I have two exiting edges, okay, labeled Fi and Fj. So first Fi and Fj have to be different. But then you know that things are going to meet again later. Okay, and they can meet in only two ways. Okay, they can make a square or they can make an octagon. That's the only two kind of patterns you can see in a crystal graph. Yeah. So for example, here, okay, if I and j differ by at least 2, okay, these things just commute, like in a symmetric group, SISJ is equal to S. So there's a whole book, okay, about crystals that you can read by Bump and Chilling, but there's some other books too by other people. So there's very nice properties of these crystals. But that's all what I'm going to say for now. Okay. So now let me tell you what's a quasi-crystal. Okay. So I'm going to fix a semi-standard Young tableau T of shape lambda. Okay. And I'm going to take the subgraph of the crystal graph that's induced by the semi-standard Young tableau that all standardize to that same tableau. Okay. So I don't think I did a definition of how we standardize a semi-standard Young tableau. Let me tell you. So this is a semi-standard Young tableau, and I want to standardize it. I'm going to read the entries from smaller to bigger, going from left to right, and bottom to left. Okay, bottom to top. Okay, so my 1 here stays a 1, the 2's become 2, 3, the 3's are going to become 4, 5, the 4, 6, 7, and the 5, 8. Okay. This is an injective map, okay, from semi-standard Young tableau. Okay, lambda to standard Young tableau object. So I read this from increasing order, and when they are equal, I go from left to right and top to bottom.
It's injected?
Hmm?
You said it's injected?
Surface.
Oh, surgery. Okay.
Surface. So if this is standard, fine upon this, I don't think sorry. Okay. Okay, so I take my crystal graph and I group together all the semi-standard Young tableau that standardize to the same standard. Okay, so here is what I did for this example. Okay, so we have this small standard Young tableau 1, 2, 3, and I claim that these 4 semi-standard Young tableau, okay, they standardize to the same. Okay, and so this is what they call a quasi-crystal.
Connected.
Yes. So actually, it's more than that. Okay. So here is the other quasi-crystal that you will get for that shape 2, 1. Okay. So the theorem is the following: that it's connected, but it's also a crystal graph. Okay. So each quasi-crystal is itself a crystal graph of another shape lambda. Okay.
Right. You say a quasi-crystal is one of these components that you circle.
Yes. So the quasi-crystal, I choose all the vertices that standardize to the same thing, and then I take the induced subgraph of the crystal that come with all these. Okay. So this would be one quasi-crystal, and this would be the other one. Okay, so that's the theorem of Mascariupi, that each quasi-crystal is itself a crystal. Okay, and then also, if I want to get the fundamental symmetric function of the composition of the tableau, okay, then I just get it by summing on all the tableau in my quasi-crystal x to the b, okay. So I get to get the f of 1, 2 here. This would be the sum of all these 4 monomials. Okay. So each quasi-crystal gives me a connected graph. That's a crystal itself. That gives me the information on the fundamental quasi-symmetric function. Okay, and also that gives me a partition of my crystal graph. Every semi-standard Young tableau standardized to a tableau. So I get the partition of my crystal. So now what's okay? Defining my object. It took me 35 minutes. I'm very efficient today. Okay, so what's a crystal skeleton? Okay, so you take each quasi-crystal and you just smash it together. Okay, so this induced subgraph, I just smash it into one vertex. Okay, and then I keep the edges between each quasi-crystal. Okay, so I have my crystal here that has 8 tableaux. Okay, I smash them into 2 quasi-crystals. And then my crystal skeleton is just these 2 vertices with just 1 arrow between them. here is the definition of a crystal skeleton. Okay, so I fix a shape lambda. The vertices are standard Young tableau of shape lambda. And now the edges, okay, because we can have, we want to understand the action of what's happening directly on the tableau. Now they are labeled by intervals of size odd. Okay. And so now here is an example for lambda is equal to 3. Okay, so let's not care about the blue cycles here. They are exactly the action on the tableau, but I can index. Now I have my 5 standard Young tableau of shape 3, 3. Okay, and that's the crystal skeleton I get. Okay, so for example, with the interval 1, 5, I can go from this tableau to this one. Okay, and as you can see, this looks very different from the crystal graph. In particular, the crystal graph is an acyclic graph, but here now we get many cycles. Okay, as you can see, here we have this cycle, but I could go also like that. Okay, now that I smash things together, now the graph looks way more complete. So these graphs have many interesting properties. Okay, so in general, rather than indexing them by tableau, we give a label to the vertex and a descent composition. Okay, and we can prove some necessary and sufficient conditions on this graph. Okay, so in particular, I can go from a composition alpha to a composition beta only if my interval, okay, so these are the parts of my composition here, and the interval must be on exactly at the border of 2 parts, okay, and just cover 2 parts of my partition. Let me tell you what I mean here. So for example, here my descent composition is 3, 3, okay, my interval is 1, 5, so my descent composition is 3, 3. To do that. Oh. Here's my composition alpha. Interval 1, 5 is okay because I can do the first half I minus union k here, and I plus would be 4, 5. Okay, so I cut my intervals into 2 halves, and they have to cover exactly 2 parts of my composition. So not exactly, because I can have more here, but at least the intervals must be covered in 2 parts of the composition. And actually, whenever this holds, okay, the edge must always exist, unless before we had an edge with certain conditions, where J was a subset of the interval I, and gamma was bigger than alpha in domination order. Okay, so that means that came from an edge. Oh, so yeah. So I write my interval like that. So I use some other notations from the paper. So I minus would be the first half. I plus m minus 1. And k here would be I plus m, I plus m. We have I'll use that actually right after, okay, to explain that not everything can happen to a composition, okay, whenever we have an edge, okay, so it means that only things in these intervals can change, and they can change only in 3 ways, okay, So or alpha is going to have still the same number of parts, or alpha is going to have one extra part, or alpha is going to lose a part. Okay, so there's only three things that can happen in a descent composition. Okay.
V is a vertex. What does it have?
So it could be the standard Young tableau.
What's the reverse?
So it's image under loose-pitch involution. So in the big crystal graph, you have something called loose-pitch involution that sends a standard Young tableau, semi-standard Young tableau to another tableau. So if I want to give all those details,
That's fine. You don't have to tell us what it is. I just
so you take the reading word, you read it from right to left, and you redo our escape. Okay. You have by reverse, I'd say reading from right to left, and then you get the bottom. So in particular, this exists on the crystal graph, okay, but they still exist on this crystal skeleton, okay. So whenever you have an edge labeled by I, okay, you can reverse everything, and you also have an edge labeled by I red, where here you just reverse the intervals and apply loose-pitch involution to the tableau. And so it's well known that whenever you do loose-pitch involution on standard Young tableau, okay, the descent composition will be the same composition, but now also read from right to left. So these graphs have many interesting combinatorial things. So I'm not going to go through exhaustive list, but in particular, what we did is we wrote axioms that characterize them in a unique way. Okay, so the same way that Stambridge did for the crystal, we can write a list of axioms that now if you give me a crystal graph, a crystal skeleton, or a graph that's labeled by composition and where the edges are labeled by intervals, I can tell you whether this is a crystal skeleton or not. Okay, so we find a list of necessary and sufficient conditions to determine whether this graph is a crystal skeleton. Okay, so we did three types, GLN type, an SN type, and a local type. So I'm not going to list them all. Let me just give you two little things about 2 and 3. Okay. So for example, what do I mean by SN branching? So here is the crystal skeleton for lambda is equal to 3 to 1. Okay. And now, so these are all my tableau. Now, if I decide to delete all the edges that contain 6, okay, so this, and this, it breaks my graph into a set of smaller graphs, okay, and these graphs will all be crystal skeletons themselves of a smaller shape, okay, namely the shape where we take off one of the corners of the partition. In this top graph here, okay, the 6 is always in this position. So if I take off this corner of the partition, this will be the crystal skeleton index by the partition 311. Okay, so here the 6 is always in this position. So this gives me a crystal skeleton indexed by the partition 2 to 1. Okay, and here the 6 is always on top, and that gives me the crystal skeleton of Shakespeare. So this is just given you on an example of 3 to 1, but it's true for every partition that if I delete all the edges that have M as a label, okay, I'm going to get a set of connected components where each connected component, okay, will correspond to all the possible corners I can take off from the diagram of my partition. Okay. So what I mean is my graph indexed by lambda, okay, would be the union, okay, of lambda, where mu is just lambda where I take off a corner of G mu, okay? And here I take off the edges labeled by n. Okay, so I just keep the edges labeled by 1 up to n minus 1. And what I get is the union, okay, of all the graphs where they are indexed by mu, where mu can be obtained by lambda by taking off the corner. So there's lots of things like that we can prove, but we can also prove some local axioms. That was actually quite hard to prove. Okay, so I told you that for the crystals, we had 2 types of possible commutation. Whenever a vertex had 2 existing edges, okay, we could only see squares and octagons. Okay. But now in the crystal skeletons, okay, we can keep the square and octagons. But now sometimes the square and octagons kind of collapse, okay, and they can become pentagon and triangles. So never hexagon, never. Okay, and another thing that's kind of cute, okay, is we have these fan axioms. So whenever we have an edge labeled by a long interval, okay, so I plus 2m, where 2m could be big, then we have all the intervals that are nested to these intervals that come out, okay? And so we can get all these existing edge, and at the end it end with a 2 cycle, and here we have a bunch of things that finish this cycle. So there's lots of beautiful structure in those graphs that tell you and necessary and sufficient conditions, okay, to build those. Okay, so that's all what I'm going to say, and what we are going to want to do next, okay, we have hope I could do that. But we're going to meet again this summer in another, or maybe a last woman in combinatorics at IES. And what we want to do now is, can we use these structures, okay, to expand the LLT in the topic. So thank you for your attention.